The final section in this pack is the breaking down of polymers, which again for the polyesters and the polyamides draws upon the chemistry that you've done previously, particularly with the esters, where if you remember the esters are reversible by putting water back in and reversing that reaction. Remember there's two types of polymers. There's addition polymers, which only have carbon bonds all the way along the structure, so carbon single bonds all the way along. And because these are non-polar, they don't attract water, and because they don't attract water, they don't react with water, so they don't break down, which is why these are non-biodegradable. Condensation polymers, however, are biodegradable, and they're biodegradable because they have polar groups which will attract water, and by adding water it's the reverse of the forward reaction. But of course, if you remember when we did this back in the carboxylic acids and the derivatives, there's two types of hydrolysis. There's acid hydrolysis and there's alkaline hydrolysis. So first of all, the definition of hydrolysis is the breaking of a bond using water. Okay, and I'll just go to this just to refresh your memory on what we talked about when we did it with the ester. So a polyester I'll exaggerate this a little bit. Would look like this, and then if I kind of put that on there as well there. So this is what a polyester would look like. I'll just kind of go around the ester group. So this is the linkage here. This would be kind of carriage number 1 if you were to look at it that way, and this would be carriage number 2 there. And remember what we've done here is we've cut the OH off the carbonyl group there, and we've taken the hydrogen off the alcohol at this point here, just to refresh your memory on what we've done up till now. Well, hydrolysis is basically the reverse of the esterification reaction, which basically means we're putting water back in. So if we're going to put water back into this, let me just kind of put this back to as it was. So if we're going to put water back into this, we are going to, as always, cut it at this point here. Once we cut it at that point there, we remove that bond. Remember that we are putting water back in, so let's put the water back in. I'll put them in red. So the OH goes back on there to give us the carboxylic acid. The hydrogen goes back on here, and I'd have the same at this end over here, and I'd also have the same at this end over here as well. Okay, so there's the alcohol and the dicarboxylic acid being made as we put the water back in. Now, the thing to remember is that there's two types of hydrolysis. Number 1, there's acid hydrolysis, which would use, for example, HCl. If we use HCl when we make the carboxylic acid, when we make the alcohol, that's the end of the story. There's no kind of anything that's going to react further that will give us a slightly different product. However, if we do the alkaline hydrolysis, then we do get a slightly different product. Again, hopefully you can remember this. So the second way that we could do this is by using sodium hydroxide. Remember, you can go back to the carboxylic acids and the derivatives and have a look at this if you have forgotten it. The sodium hydroxide is a catalyst, so it comes out unchanged. So once the water has gone back into the polyester to give us the dicarboxylic acid and the diol here, the sodium hydroxide reacts with the carboxylic acid to metal hydroxide, reacts with an acid to form salt. So these here are going to be replaced with the sodium salt. So I get an Na there, and I'm going to get an Na here as well. And hopefully you remember that. And of course, I've done a dicarboxylic acid and a diol here. It would be exactly the same if it was so let me we do it as part of a polymer. So C O O R C O R. Okay, so again, sticking to what we know, we break it here, which means that bond is going to disappear, which means the water is going to go back in. So here's the water, OH back on there, and the hydrogen back on here. And of course, this would happen over this end as well. OH back on there, and the hydrogen back on this thing here. Now, if we did it with acid hydrolysis, no further changes. However, if we used sodium hydroxide, that would then react with the carboxylic acid, which would then give us the sodium salt of the hydroxycarboxylic acid. So that's that for the hydrolysis of the polyesters. Okay, so and in the notes we've got that here. Okay, so we break it there. Oh, hang on, we break it there. Remember, we put the water in first, which will give us our alcohol and our carboxylic acids. If it's acid hydrolysis, we're done. If it's alkaline hydrolysis using sodium hydroxide and water, the sodium hydroxide, which is a catalyst, will then replace the hydrogens in the carboxylic acids. Okay. The polyamides, it's a similar story, but we need that. There's an extra problem with those. So again, I'll just do this with. Okay, and so on and so on and so on. Okay, so that would be a C double bond O. So as always, we would cut it at this point here. We would put our water back in. So let me get rid of that. And let's put the water back in. So the OH goes in there and the hydrogen goes here. Now remember, there's two types of hydrolysis that we can do. Number one, we can do hydrolysis using hydrochloric acid. Now here's where it is slightly different, because hydrochloric acid, if you remember, reacts with the amines here. So just down here, just to refresh your memory, R NH2 plus HCl will give R NH3Cl. So when you're doing the acid hydrolysis with this, the product that you get is always going to be the salt of the amine. So at this point here, it's not going to be NH2. What we're actually going to have there is, I'll do it in green, is H3N, and there's going to be a positive charge on there. And of course, there would also be a chloride knocking around in there as well. So that would be what you would get if you did the acid hydrolysis. So because it's acid hydrolysis, the water goes in, the hydrochloric acid is a catalyst, so it comes out unchanged, but then the hydrochloric acid catalyst will react with the amine to give you the salt of the amine. Okay. If we did it with alkaline hydrolysis, so that's the sodium hydroxide, let's just pop this back as it was. So we have the N, H and H there. So if I was doing this using sodium hydroxide instead, it's exactly the same as what happened with the polyesters. With the polyamides, the sodium hydroxide, it's a catalyst, it comes out unchanged. So as soon as the water has hydrolyzed the amide, the sodium hydroxide then reacts with the carboxylic acid group here. The OH would come off and an Na would go on instead. And again, this is highlighted down here. So with the polyamides, just like before, we would cut it through this part here. We put the OH back on the carboxylic acid and the hydrogen back on the amine group. If it's acid hydrolysis, you can see here, look, that we get the salt of the amine. And if it is alkaline hydrolysis, we get the salt of the carboxylic acid. The final bit in here really is about the degradability of these polymers. There's several ways that we can get rid of polymers. They are globally a problem, and that's because they generally are not biodegradable, which basically means if you bury them in the ground, they just stay there. And in the past, we'd bury our rubbish, it would degrade, and then that site would be fine in 50 or 100 years. But these days, when we fill polymers, or particularly addition polymers, in the ground, they don't degrade, and that land cannot be used again. And of course, eventually we will run out of land. So there are advantages and disadvantages to every method of disposal. However, there is no quick fix or easy solution to any of these. So the most common one really is landfill. It is very, very cheap. However, non-biodegradable things don't decompose. Some of them that do decompose very often give off greenhouse gases such as CH4, and if they've got chlorines in there, then they can give kind of water-soluble toxins, which would then eventually kind of leach away into the water cycle. The second way of doing it would be to burn it. And if you think about it, it's come from a fossil fuel in the first place, and we burn fossil fuels anyway. So if you could break the polymer back down into its smaller monomers, it would actually be quite a good fuel. So in terms of being a fuel, it's great. It would produce heat energy. However, like all fuels, you're going to get all of these that are given off as well. Styrene has benzene in it, which is terrible when that is given off. And any polymers that have chlorine on there is going to give off HCl gas. Again, that would need removing as well. Really, the best way to deal with our plastic problem is to sort and recycle. The problem with this is it is incredibly expensive because there's loads and loads of different types of polymers that we use for different types of packaging and carrier bags. And there's no easy way to separate them out. And if you want to reuse them and remold them, you've got to make sure that you've only got the one type of polymer. So all polymers have a code on them, but they literally have to be sorted by hand. So you have people stood along a conveyor belt that literally pull these off and then put them in certain bins, which they can then be reused. It's very, very costly, and it's actually cheaper to make brand new plastics from crude oil than it is to sort and recycle old plastics. And I think, that is pretty much that. So again, some questions there for you to have a go at.